Mohammad El Wali is a postdoctoral researcher at the University of Helsinki. His research focuses on food transition models and the impacts of future food systems on the environment. Please, Mohammad.
Yes, hello everybody, and thank you very much for the invitation. I'm also part of the Future Sustainable Food Systems Research Group in the university, where we are continuously trying to investigate the environmental performance of food products, and including also novel food technologies and cellular agriculture. And in this presentation, I will talk about the projected environmental and to some extent biodiversity benefits of cellular agriculture on the European scale. The results, of course, are what we have been working on in our group specifically. And some of the results are preliminary results that are still under development as well. Of course, you have already been seeing that there are a list of or several environmental impact comparisons between several protein sources and livestock products and plant-based protein products as well. And this figure, of course, provides sort of a general overview of several LCA studies that have been conducted. And generally, the very first impression that we can get from the LCA studies is that there's always less land use, of course, for cellular agriculture products, and to some extent also less greenhouse gas emissions, of course, depending on the energy source in which cellular agriculture has been produced. But the issue that we tried to look further was to look into the... Okay, so the text has been bigger than I expected here. But the question that we're trying to answer here in this presentation is what are the environmental implications of replacing livestock products with cellular agriculture? And this is a little bit different than the product level LCA assessments, because here we are trying to look at the implication on the system as a whole, because in previous studies what we've been doing in LCAs, we were trying to take the livestock products out from their system and compare them with cellular agriculture also out from their system. But if you look in reality, you will find that cellular agriculture products and livestock products are all embedded in a very complex system where there is a lot of causalities and interdependencies and feedback loops also. And of course, it's also dynamic, mainly triggered by time-dependent variables, including population growth, dietary preference changes, and so on. So, of course, we will. There's no possibility to include all cellular agriculture products. So, in this presentation, I will talk about two case materials or two case products that has already been studied before. And microbial protein, for example, is what Solar Foods is producing, which requires hydrogen oxidizing bacteria and is totally decoupled from agriculture. But if we look into cell culture, recombinant proteins, it's a recombinant protein that requires fungus and also glucose as a source of carbon, so it's partially dependent on agricultural inputs or whatever agriculture crops that can produce starch or glucose to be fed into the production process. Now, the very first findings that we found was that the global energy demand for a transition to cellular agriculture is definitely higher than the business as usual scenario. And this was partially due to the country level differences across the globe in grid mixes, and also generally the high electricity or the high energy input or the high energy demand for the cellular agriculture products. So we thought it made a lot of sense, of course, to power this transition, this hypothetical transition. Of course, it's important to press that a full transition to cellular agriculture is not likely to happen in the next decades. But what we're trying to see here is the maximum level of changes environmentally, just for policymakers to have a look on what's going on in the future. So here we deployed in the analysis solar energy and wind energy as two most rapidly increasing in terms of capacity. Of course, there are other low carbon energy sources such as nuclear and others, but for now these two sources are most rapidly increasing. So we put them as main energy source to power the transition, or the global transition to cellular agriculture products. Now, of course, the question that we needed to answer during the research was, does the future, or does the projected green energy capacity levels globally are sufficient for global transition to cellular agriculture? Globally, of course, you can already see that there are some countries where the projected transition to cellular agriculture to replace livestock products might require at least 100% and sometimes even more. On the other hand, if we look into the Europe, mainly EU and EEA member states, there are several countries where, of course, the demand for green energy might be between 20 and 60. And so if we take the whole Europe as one system, which means that the whole member states are actually collaborating with each other, we could say that there is around 32% of projected green energy that will be demanded for the transition to cellular agriculture. Of course, this is all dependent on how the green energy is allocated from the perspective of policymakers. 32% is quite high, I would say, in terms of energy prioritization, to which sector should green energy go to. And in this case, we are allocating this 32% for the food system. That embeds also the transition to cellular agriculture. Just a few words on the global shares. So within the constraint level of green energy capacity levels in the future, in 2050, Europe is expected to contribute around 15%, of course following China and the United States, which still are the main contributors for cellular agriculture products. And that's, of course, for two main reasons. First reason is that they are expected to contribute to the highest capacity levels in terms of green energy, and particularly wind and solar energy. And the second reason, of course, is that these two countries are top livestock producers anyway, so their country level replacement will be the highest in that terms as well. But if we look globally also, there is a 72% maximum transition to cellular agriculture given the constraint level of green energy capacity levels. Of course, in this research, we also included the capacity levels of critical materials that are needed for the wind turbines and solar photovoltaic panels. So this constraint of critical materials or critical material scarcity can further reduce this 72% transition as well. But I thought I will focus only on the environmental impact in this presentation. So going to the environmental results, the very first impression here is that there is already a decrease in greenhouse gas emissions, which is very much understandable if we, of course, consider the livestock methane emissions. In the business as usual scenario, it's already a little bit declining, and that's also partially depending on the dietary switch of the citizens in EU and EEA countries. We can also see that nitrous oxide, which is originating from fertilizers application, is also decreasing with around 25% contribution to the total reduction of greenhouse gas emissions. And this is, of course, because we still need some feed croplands for the cellular agriculture products, such as the recombinant protein. But still, even with that increase in these cropland that is needed for glucose, we still have a net reduction of greenhouse gas emissions, and particularly in nitrous oxide as well. And of course, you have the manure management-based emissions, which is, of course, you can say a byproduct of livestock grazing and production. And it's also very much interesting to see that if we think about the whole system, so when you are reducing livestock production, you are also reducing manure. So intuitively, you would think that we will need more chemical fertilizers from synthetic sources, which might, of course, increase the environmental burdens. But we found that this is not the case, as feed croplands require almost more than 40% of the fertilizers that are being fed to the soil. So this makes a good trade-off, actually. So even with that, the net reduction is quite visible. If we look into the land use environmental impact category, we realize that there's also a significant reduction. This was very much expected also, because the cellular agriculture production requires not that much land compared to the livestock grazing, and also feed cropland for livestock production. And even with the land needed for solar photovoltaic panels and also wind turbines, there was a net reduction as well, and also including the cropland needed for glucose production. So even with all of that, the net reduction was still quite visible. And in the European scale, of course, feed cropland could 68% of the total land reuse reduction was contributed to feed cropland elimination, and the rest was contributed to the pasture or livestock grazing lands. Now, the paper or the work that we are working on right now, hopefully in the last stages before submission, we are trying to incorporate the land savings that we've been obtaining in previous publications. We are trying to use that land saving in assessing the biodiversity impact by quantifying the species richness or the species loss also of terrestrial taxonomic groups. And for that, we are modeling the land use change system. We have several land types, such as pasture, forest, urban land, cropland, and other types of lands as well. And we are deploying, or we are using the GLAM method developed by Scherer et al., where they try to quantify or characterize the potentially disappeared fractions of terrestrial taxonomic groups. And their method, of course, is dependent on several variables. First of all, the intensity levels in which this land is transforming to. So if they are transforming to forest, what is the intensity level of these forestation activities? Or otherwise, if they are going for cropland, what is the intensity level at which cropland is being used, and so on. And the second factor that they are using in their quantification method is the type of land that we are transforming to. So transforming to forest has different species loss than pasture, understandably. And the third variable, or the third factor that they are trying to that they are using for the quantification of the potential disappeared fractions is also the ecoregion, or the geographical scope. So, for example, if you try to go for species loss in Brazil, it will be different than species loss here in Finland, because the species richness levels is very different. Where in Brazil the species richness per meter square, of course, is much higher than here. So the species loss, of course, is much higher. Now, what we are trying to do is, as I said before, we are trying to model this land use change system. Now, of course, one of the most important things, let's say, for example, we have been looking at previous land use savings, and we saw that there is a reduction in pasture and cropland. Now, the most important thing that we need to find out is not only that we have land savings. This should not be the objective. Rather, this is sort of an incomplete step to go for biodiversity recovery. The main thing that we should focus on is the destination of the land to which transformation is happening. So, if we are saving pasture and croplands, to which type of land will that area go to? Will it go to forest, for example, through forestation activities, or will it go to other land types? And here is where we are trying to build up some land use change scenarios. Of course, forestation is, or managed forestation is kind of easiest way to quantify the biodiversity impact, because we already have results from that GLAM method on biodiversity impact. But also another ideal situation would be rewilding, which is even more effective and efficient than forestation, where you are just promoting complex self-sustaining ecosystems by restoring natural ecological factors while reducing human control. Because even in forestation, if the forestation activities are poorly managed, you might actually exacerbate the environmental or the biodiversity impact and exacerbate the species loss as well. Another third scenario, which is other management practices, for example, where the land can actually go to other types, such as urban land, for example, if the urbanization is so much going in a high pace that you actually need to expand urban land, and so you are prioritizing urban land expansion over other forestation on rewilding activities, even though this is not really the case in Europe, I think, based on our results. But so eventually the question that we try to answer here is, does transition cellular agriculture reduce species loss below the safe operating space? There's also this, we already know from our preliminary results on working right now that there's reduction in species loss, which is good, and so we are restoring biodiversity levels. But the question is, do we actually restore these biodiversity levels to levels under the or within the safe operating space? And this is very important, because as far as the impact is still above the safe operating space, then there are still needs to be managed urgently. And we are actually trying to, this is very much similar, or actually the same idea about planetary boundaries figure, which I'm sure you already know, where there are a lot of environmental indicators that are already surpassing or exceeding the boundary limits, or the planetary boundary limits, such as water use, carbon emissions, eutrophication, phosphorus eutrophication, and even biodiversity as a whole. They are all exceeding the planetary boundary limits. And the same thing here we are applying, that we are trying to see how this transition cellular agriculture incorporated by land saving, and also the destination of that land saving, can actually reduce the biodiversity below the safe operating space. Yes, thank you very much.
Do we have questions? Okay, there. Well, I'm on my way, so can I give you first?
Thank you for a very nice talk. You had this notion about clean energy, and you'd consume, in my opinion, quite a lot of it. Do you have any considerations on trade-offs? I'm going to brew in a premise in this question, and is that there will only be a finite amount of clean energy that we manage to make here in Europe. And the cars and the central heating and the industry are probably also going to want this clean energy. So have you thought about the trade-off between giving a kilowatt to industry, a kilowatt to transportation, or a kilowatt to cellular agriculture, considering the fact that if we give it to cellular agriculture, the guys in industry may burn something fossil? Thank you for a really nice talk.
Thank you. Unfortunately, we could not go that way, but the most we could say that it would require 32% of Europe's projected low-carbon energy sources. But this, again, it depends on the policymakers, so we did not really go into the allocation strategies of clean energy. But if we actually look into that work, we also did some gradual transition cellular agriculture, so not necessarily a hypothetical full transition, but also 10%, 20%, 30%, 50%. So this can give more idea on how green energy could fuel the transition cellular agriculture. Of course, not necessarily 100% of transition agriculture can go through green energy. Some other fossil fuel can also be used to some extent if necessary. Thank you.
Okay. My question would be about the biodiversity effect. So you considered the effect of cellular agriculture on biodiversity, but when I was looking at your slides, I noticed that there is quite a large increase in renewable energy kind of required. So have you considered the effect of this renewable energy on biodiversity? And this is at least in Finland, it starts to be quite a big question that how do we manage the biodiversity issues related to especially wind energy?
Okay, thank you very much. Well, if yes, indirectly I would say yes, because what the type of modeling we did use was that we, for example, here we already are modeling the system, yeah, and so when the biodiversity changes as you go from one land type to another, and when we are referring to the establishment of solar photovoltaic panels or wind turbines, we have already removed this area from forests, for example. So when we are referring to biodiversity restoration from forestation activities, we have already excluded the wind turbines and the land needed for wind turbines and solar photovoltaic panels. But I also understand that there might be beyond land indicators. For example, the noise pollution of wind turbines might also be might also have a severe effect on biodiversity and emigration of species as well. But unfortunately, now only the main indicator is land use transformation and not other.
Consider nuclear power?
No, we did not.
Why?
Explained it.
Okay.
Yeah.
Sorry.
I would still say it's a valid question because nuclear power is the largest source of low carbon in Europe. And here you make it seem like it's a very big chunk of renewable energy that we need. And then you yourself referred now in the questions to low carbon energy, and then actually our pool is a lot larger because it will increase. So I think it would be very topical from the research point of view to take this into account as well.
It's a good point. Though we actually the work we've been doing on globally, so we took the global pace of increase between each low carbon energy source, and wind and solar were the most. But if we take Europe as a case itself, yeah, maybe it makes sense. Yes. Yeah.
Thank you, Mohammad. We're going to have a panel discussion next. Let's give a hand first for amazing speech.